preserve and conserve our cultural heritage. So we started a couple of weeks ago with the first webinar, where we learned a little bit more about the project, how it was born, the concept, the main concept that are behind ARTEMIS and the digital twin, the heritage digital twin ontology. And if you missed it, you will find it both on the project website, on the ARTEMIS project website, and on the ARTEMIS YouTube channel. So feel free to have a look to learn more about the project. Today, we will together try to understand a little bit more the relationships between the reactive digital twins, ontologies, and artificial intelligence. We will do so with our colleagues from the Ariadne Research Infrastructure, ISBL, and I'm pleased to leave the floor to Achille Felicetti, who is responsible for the data infrastructure in ARTEMIS, including the development of the knowledge base of the Reactive Heritage Digital Twin ontology. So Achille, floor is yours.
Okay, thank you very much, Claudio, for this introduction. And good afternoon, everyone, and thank you for joining us in this webinar. It's a real pleasure to have the possibility to share with you the results of our work, which we are very excited to share. So this presentation, my presentation is intended fundamentally to provide some brief introductory notes to the reason why we are using ontologies, knowledge graphs, and the innovative technologies of artificial intelligence for empowering the heritage digital twins that we are developing in ARTEMIS. Mine will be just an overview, let's say a philosophical background. The technical details will be shown afterwards in more depth by my colleagues Aida and Miriana. Together we work in ARTEMIS, and our activities are carried out under the framework that we call ARTEMIS Data Infrastructure, which is a digital platform designed mainly for hosting the complete inventory of all the knowledge about the cultural entities that we want to study and to preserve, together with the information about the technologies and the tools that we are going to use in ARTEMIS to build smarter and more powerful digital twins. So let me start from here. That is from the definition of what a digital twin for cultural heritage actually is in our perspective. This was the topic of the first talk in ARTEMIS, but it's worth repeating it for the sake of understanding what we are going to explain. So in ARTEMIS, we have defined digital twins as the complex of all available knowledge about a certain cultural entity, and especially the knowledge relating to its history and the various events in which this cultural entity was involved during its lifetime. We also consider very relevant the material and structural aspects of cultural entities, especially together with their environmental conditions, and also the data produced by the technical and scientific investigations that are usually carried out on cultural objects for the sake of preservation and conservation. So cultural knowledge is the name that we give to the knowledge that we collect, actually represents the non-physical, the immaterial side, the immaterial part of cultural objects. And this immaterial part is extremely relevant. It's an aspect very important, since in our perception, it is precisely the knowledge surrounding a cultural object that frames its identity and shapes its nature. So this immaterial component actually makes an object cultural, so gives the cultural significance to what is just a physical object otherwise. So we can even go further and maybe dare to affirm that the cultural entity is such precisely by virtue of the immaterial cultural value, which is given to it by its history and by the relevance and the significance that it assumes, for instance, for a certain community or as part of a given tradition. And this concept of tradition, this idea, is something very important for us. It's an element that animates our work and our research. In fact, what we do is not to seek knowledge for just for the sake of collecting and preserving valuable information, even if also this is a very important activity. But we operate keeping in mind and taking inspiration from the words of Gustav Mahler that you can see here. What we want to achieve is not the worship of ashes, but to preserve and keep the fire of knowledge fervent and alive, which in technological terms means that we want to use knowledge for turning on and activating our digital twins, and for transforming them into living and reactive system. This is quite important because cultural objects themselves are entities whose life unfolds over time and through complex series of events. And it is precisely the knowledge of these events that allows us to develop a sort of digital memory that can make our systems more reactive and more powerful. So this kind of memory is a fundamental element to be taken into account, especially when we consider that systems without this kind of memory are just static systems in which predictive capabilities are in a certain sense compromised by the fact of relying just on the current state of affairs, state of things, and thus on the complete ignorance of the effects of previous conditions. But as it is well known, in every system, the current conditions are always the result or are influenced by previous events. So in this perspective, only memory can enable our systems to use the knowledge on the past for making reliable projection and forecast of the future, of future conditions especially, and of future states that we want to foresee. So just to summarize this important concept, we can say that knowledge and memory are essential elements to transform our digital twins into reactive digital twins. And reactive digital twins means dynamic systems that, based on the collected and past information, are able to mirror the present condition in a faithful way, but also to make precise and accurate simulation of future scenarios and future behaviors. But, of course, as often happens, there is a button. And in our case, it concerns the fact that knowledge is not always immediately accessible nor useful, especially in conditions and formats that are understandable by machine and can be suitable to be used by digital twins. It is like, you know, to going around in a dark forest. I also took this expression, Mirkwood, from Tolkien, because he used this word to indicate a very, very dark and intricate forest. Is the situation, is a similar situation that we face when we are looking for knowledge. Especially knowledge about cultural heritage, which is dispersed and hidden in various documents, books, archives, papers, various kinds of documentation. And in many cases, it is even not written at all, but just lives in the memory of people. So even more difficult to be accessed and retrieved. But it is actually maybe not a coincidence that our project has the name of the Greek goddess of forests and the hunt, And it is precisely with this in mind that we use ontologies and artificial intelligences as if they were, let's say, the weapons of the goddess, the arrows and the bow of Artemis. And with these powerful weapons, we can go for hunting the pieces of information that are hidden and dispersed in order to retrieve them in the smartest possible way, and we will see how, and to capture and collect them, and finally to structure and wave them together in order to create the digital mind of our digital systems. This will create also the historical memory of all the past conditions and the past events that we mentioned before as a key element for our study. So let's very briefly introduce the two cases that will be presented afterwards by Aida and Miriana. These are intended to illustrate how it's possible to retrieve this knowledge using the available technology. The first application case, which you will see in the next presentation, aims to go, let's say, from words to knowledge, since it has the aim of using these sophisticated tools and technology to identify and, in a certain way, distill relevant knowledge from textual documentation, and then putting this distilled information in a standard format by means of the ontologies. So this is a very important operation because, as we know, much of the knowledge on cultural heritage is embedded in textual documentation. So it's not just documentation, it's even not structured. It's textual, it's expressed in free words, so even more difficult to capture and retrieve. It's the knowledge that we can retrieve in narratives, in the chronicles, the historical account of the facts, the literary sources concerning cultural objects and events, and as we say, also in the technical and scientific documentation. So what we do is to use artificial intelligence for extracting this relevant information from texts of various kinds, and then processing, transforming, working on it in order to put it in a suitable format to populate the knowledge graphs that are designed to become the memory of the digital twin. We have verified that actually artificial intelligence is very, very smart in this task, and that it can simplify and speed up these tasks in ways that were unthinkable until a few years ago. We were very surprised of the efficiency of this technology, and you will see them in the next presentations. But of course, this process is supposed to take place in controlled environments. So we don't leave the artificial intelligence completely free to go in the woods and retrieve what he wants. What we do is try to direct its activity. And first of all, we use technologies that are under our control, technologies that we ourselves have designed, configured, and trained to do this job. This is what we call a supervised process, and this is a fundamental step because artificial intelligence are very powerful, but as we know, power is useless or even dangerous without a valid control. And the control in our case is always in the hands of scholars, in the hands of humans, in our hands. Ontologies, of course, also play a fundamental role in this process because they provide the linguistic settles, the linguistic basis and the grammar, the formal grammar and syntax to express all this knowledge in unambiguous ways. So just to give you an idea, I don't want to go into technical detail here, just to provide you with an image of how an ontology could look like. I want to show you an example of how formal ontology can be used to shape different fragments of knowledge so that they are semantically linked to each other by means of what we call relationships. This is a type of structure, is actually a sort of network of information that allows us to generate multidimensional knowledge graphs, very complicated structures, capable, for example, of integrating, as in the case that you see here, data deriving from scientific analysis on your left-hand side with information about the physical nature of the investigated objects. By means of the same semantic tools, properties, and relationships that you see here represented as lines with some names, it's also possible to link valuable information concerning people, places, times, event, tools, and the techniques, for instance, that in this case are used to perform the various activities in a very smart way. Of course, what you see in this slide is just a fragment of a graph that, as I said, could potentially assume enormous proportions. But nevertheless, these complex graphs never become chaotic. They are ordered, they have an internal order in which each fragment of information is linked to the others in a very, very precise and meaningful way, in a sort of harmony of the spheres, which links the information together. And finally, all this knowledge is expressed in a format suitable to be used by both humans and machine. So, for instance, you can read what is written here, but the formal language that is used for expressing it in the language of the machine makes it also available for machines to be understood, to be read, and then to be reused afterwards. So the second application that you will see, also very, very interesting, and you will see how, follows a sort of inverse trend and working in the opposite direction, moving in a certain sense from knowledge to words, but in a digital fashion, because the words in this case are digital words, the words of the artificial intelligence. So as we have seen, ontologies are designed to make information usable by both humans and machines. And in this sense, they can constitute a sort of lingua franca that can be used not only to express knowledge in a structured way, but also to establish communication and to communicate information to the artificial intelligence using a format and a language that is closer to the artificial, let's say, language that artificial intelligence use. In this way, it's much easier for the artificial intelligence to understand the real meaning of the provided information. This is a sort of semantic illumination. We call illumination because provides the artificial intelligence with a clear vision on the data. And this illumination is a process that makes artificial intelligence aware on every level of crucial and vital information, including the context in which events unfold and in which objects live, and also the different semantic connection existing between the various fragments of information that we mentioned before. But above all, this process has the great advantage of minimizing the well-known issue of the hallucinations that artificial intelligence typically manifests when they are used. So mitigating these hallucinations will have the benefit of getting clearer and more reliable information from the artificial intelligence when they are consulted, they are queried, and most importantly, when they are called to assist heritage digital twins and the scholars to make important decisions, for which clear information is paramount. And this goes towards the conclusion of my presentation, which, as I said, was a sort of overview of what you see afterwards. Just to say that artificial intelligence can be activated on different points of the pipeline of the knowledge extraction and use, and can operate in different but complementary directions. So on the one hand, they can be used, as we saw, for absorbing and elaborating the knowledge they acquire. And on the other hand, they can be trained and queried for providing relevant answers to complex questions. In many sense, they can be considered as a bridge between the real and the digital worlds, and as a smart intermediary between humans and machine. In fact, they can be used also by machine alone in a machine-to-machine communication, for instance, via APIs, with other digital interfaces like sensors, actuators, and so on. And also in a machine-to-humans interaction, allowing humans to query the knowledge graphs using natural language. This is what Aida will show. To do this, we will use tools that we are familiar with, that are entering our life, like the chat-style interfaces used by ChatGPT, for instance, or Gemini, or other popular artificial intelligence today. In both these cases, the goal is to obtain clear answers based on the reliable knowledge and the control data that supports and implements the complex systems that we are developing. And they have a name. They are called as cognitive digital twins. And these are the evolution of digital twins empowered by ontologies and artificial intelligence that we are planning and we are developing for extending the capacity of digital twins and assisting and enabling also the simulation operation and the prediction operation typical of the digital twins. Of course, we don't want to create oracles, okay? What we want is not a system that is able to predict the future with absolute certainty. In fact, we actually ask to machine not for sort of prophetic divination on the future, but we want to build smart systems that are capable of a sort of approximating the future, or the different possibilities that the future will provide to the best of their ability. And this can be achieved by means of the knowledge that we will be able to retrieve and of the technology that we will be able to develop and to deploy. Okay, so my presentation stops here. That's all from my side. Now I leave the floor to the exciting things that will be shown by my colleagues. And for the moment, I thank you very much for your attention.
Thank you, Achille, so much. Before giving the floor to Miriana, Aida, let me just remind all those who are following us both via Zoom and YouTube. We have been said that we have a lot of people following us on YouTube, almost 650 people following us. So thanks so much for your interest. So if you have any questions or any comments for our speakers, feel free to ask them either via YouTube, if you are following us on YouTube, or via the question and answer feature in Zoom. The chat is disabled, but you can use the question and answer feature. So feel free to pose your questions, and we will have some time at the end for discussion to answer those questions. Let me also remind another thing before leaving the floor to Miriana, which is our survey. So for those of you who have not yet contributed, we extended the deadline of the ARTEMIS survey. You will find it on the project website. On the top menu, there is the menu item about the survey, and we will post the link on the chat and on YouTube as well. So this helps us a lot to shape the infrastructures and the services that we are developing in ARTEMIS. So we kindly ask you to reserve us 5 minutes of your time. It's very short and easy to answer, to complete the survey, and your contribution is highly appreciated. Thank you so much. And I now leave the floor to Miriana for the demonstration.
Thank you, Claudio. I hope you can hear me. Thank you also, Achille, for the presentation and introduction. I'm going to talk you through one of the technical aspects, hopefully without being too technical. So how can we go from unstructured data, mostly textual, but not only textual, to structured knowledge in order to feed graphs and ontologies in more efficient and fast ways, together with the help, of course, of AI tools. You can pass the slide. Thank you. So as Achille already mentioned, a lot of real-world data as of now is composed by unstructured text. So that means documents, reports, articles, logs, notes, whatever. But unstructured text has a lot of problems and a lot of issues from the machine point of view. It's often inconsistent, noisy, and semantically ambiguous. Part of it because it's written in natural language, which is semantically ambiguous on its own. And it's also difficult to process all this data because the manual processing of the textual data is inefficient, takes up a lot of time, error-prone, and non-scalable. On top of that, the data is scattered across multiple sources and written in different languages. So these are all complexities that adds to how can we find out the relevant information inside the text. Passing to actual cultural heritage data. So the next slide. Today, cultural heritage data is composed by a number of different sources and types. So it's vast, diverse, and often unstructured, as I already said, and it includes, yes, text, papers, and reports, which can also be old ones or heterogeneous, but also images of buildings and artifacts, photos or drawings, images of scientific analysis or scientific analysis on their own, such as XRF or spectroscopy, so scientific analysis that goes really into detail and are not easily understandable, and also tables, PDFs, and notes from different specialists. This complexity arises from a lot of elements, of course, particularly from different documentation methods. So an archaeologist can have different methods than a painter or a sculptor or a 3D expert, and legacy data, of course, and the mixed media formats and file types. As a result, we are in the front of an information chaos. So the data is rich, there's a lot of data, but it's fragmented and disconnected. How can we try to find a structure inside it? For the first problem, so the scattering of the data, we tried to scrape the web. We didn't actually scrape the web, and we did the scraping, not the crawling, which is often illegal to do. We stayed legal, and we scraped Ariadne RE website, which is an archaeological online database that provides a lot of archaeological data to test this process if it was feasible or not. So we were successfully able to automate data collection from the web pages by simulating real user behavior. So what a web scraper does, for those of you who don't know, is going into the web pages and looking inside those web pages for some things that the code tells them to look for. In our cases was PDFs links. So we use Selenium, which is an open source web automation framework, and is useful because it can scrape dynamic website. So if the website incorporates dynamic tools or add-ons or plugins, it is successful anyway. And we were able to automatically script a number of pages, so multiple pages, not just the first one, navigate them and extract the PDF links. From the PDF links, we didn't care what was written inside the PDFs at that point. We just wanted all the PDFs, and we downloaded automatically the PDFs, so without going one by one, clicking download everything, and automatically extracted the raw text from the PDFs and also the images. So this is one way we can fasten up the whole process. But what if we already have the data, the written one, the textual one, and we have the raw text? How can we transform it into structured data to provide an efficient backbone for the heritage digital twins, which is, as Achille mentioned before, knowledge graph. Knowledge graph are the ideal way of course, storing cultural heritage assets and information, because they're able also to provide semantic depth, which is fundamental for, of course, our type of data. In this case, they are able to work multilingually and also preserve some meaningful information, such as the provenance of the data, and linking the data. They can also perform reasoning and connecting data which can seem to be not connected, but actually they are. If we can move forward, thank you. The actual problem of building knowledge graphs backed up by ontologies is that you need to have technical knowledge, both about knowledge graphs and about ontologies, as the one that Achille showed you is just one example of one ontology and a part of one ontology. So imagine being an archaeologist or a 3D expert and needing to encode all the information you have in your data in that format for multiple ontologies and multiple data. That is almost impossible. So it creates a bottleneck, the manual annotation part, because it's slow, manual, and require expertise. And most domain experts have the data, have their domain expertise, of course, but they don't have the tools or the specific knowledge to annotate them in the right way. So what we thought of trying to do was to build an AI assistant that could help you automatically or semi-automatically tagging the relevant information inside the text and putting them in the right format for them to be successfully injected into a knowledge graph and build a knowledge graph in a faster way. If we can move on, thank you. Okay, so what we are actually doing here is a really brief explanation. We are taking the raw text, extracting the terms with the help, of course, of large language models, but not only, having a validation step for these terms, and then being able to extract the RDF triples, which is the grammar and the language behind the ontology, as Achille was explaining before. How are we actually doing it? So we pre-process the text using Spacy, which is open source library that everybody that works with NLP knows, to segment and clean the textual input. Then we firstly performed concept extraction using Mistral 7b because it's open source. We wanted only to use, of course, open source models to identify in an automatic way key scientific terms and concepts that could be valuable for ontologies. After that, we semantically grouped them via sentence transformer or cosine similarity. So it was not just string matching, so actual word equals an actual word, okay, they are the same entity, but we added the semantic part. So words with the same meaning, even if it's written in another way, can be grouped together because they have the same meaning. Then we validated the terms and also used context retrieval with the help of a vectorial database that is FAIST, also open source, to ensure an accurate and context-aware RDF triple generation. And then we did like another round with the large language model, still Mistral 7b, to produce actually the RDF triples aligned with the domain ontologies, which are usually CDOC-CRM, AUCAT, CRM-HS, and the ARTEMIS ontology, which is the one that Achille and his team are actually developing. So this approach can actually be a game changer because it speeds up the graph creation by a lot of time. It is usable by non-technical experts because all the coding part is done backend. So people can go and just like put into their documents and the whole process is done backend. There's no coding required and is compatible with different ontologies. It can also be reused because it works across domains without the needing to retrain. So without adding more computational timing into the process. And it also combines the AI with an expert validation to avoid the risk of hallucination as more as we can. Okay, this is a small video that is supposedly supposed to help. So the actual normal process is we open the textual documents, scientific reports, and so on, and by hand, we find out inside the documents all the relevant information, all the concepts that could be relevant. But this is, as you can see, a slow and manual process. Just to go through the abstract, it takes a minute or more. Imagine when you have a lot of documents. Can be done in multiple languages and requires prior knowledge, as we already mentioned before, of the ontology by the end user. So what we were able to do is to go from this one to actually extracting the raw text on one side automatically and also the images on the other side in an automatic way that takes up, I don't know, not even 1 second. From this, we were actually able to structure all that information in a turtle file, so that is ready for the knowledge graph ingestion. And from that part, we can also visualize the graph. We use GraphDB that provides an interactive and semantically rich representation of the original documents. This done by hand would have taken a lot of time, of course, and expertise that, of course, people usually don't have. So this was our approach for the textual documentation. But what about the images? Because as we saw, a lot of, we can pass the video now. We can go to the next ones. Thank you. And as we saw, a lot of scientific reports about scientific analysis also contain images about the actual analysis itself, especially in cultural heritage nowadays. Research produces diverse scientific analysis images, such as XRF spectra, plots, restoration workflows, architectural plans, a lot of images that are not easily understandable by people who are not inside the field. And these images are also often embedded inside an unstructured PDF, and there is a lack of standardized metadata and semantic context. So what if we can automate the extraction of analysis types and semantic meaning to fuel digital twins and knowledge bases also for the images? So we are trying to develop also this pipeline. It's still, of course, ongoing process to be able to identify in an automatic way the type of scientific analysis that is shown in the research figure by also using open source and EU compliant AI models to keep transparency and accessibility. Our scalable pipeline combines vision language models, which are large language models that can also accept as inputs images for image classification and semantic understanding, which could not be done just by using, for example, object detectors, and combining them with the FICE-based vector database for the vectorial search, the same one that we mentioned before, for similarity retrieval and knowledge-based linking. So this process extracts the images from the unstructured PDFs, as I already shown you, and then performs zero-shot classification using OpenClip, which is a vision language model open source that is able to generate the image embeddings. What are the embeddings is the semantic value of the image that can be stored in a specific database to then be retrieved when needed, and index them for fast similarity search. And then we can automatically tag and index the images also to enrich the digital knowledge bases. The future plan is also to fine-tune the model, so to make it more efficient on actually our data set and the cultural heritage data to boost the recognition of the domain-specific figure types. So what is good about OpenClip is it is also fine-tunable. It's not just that, and you cannot do anything else about it. So also, this process has a lot of benefits for the cultural heritage digital twins, because the approach is able to automate both the extraction of the text and the figure context and analysis type, not just this is a picture and in the picture there is a painting. Both from scientific literature and raw analysis, it doesn't need to be, the image doesn't need to be inside a PDF. It can also be the image on its own. And it can also deliver semantic annotation to enrich the digital twins of cultural assets and facilitates the integration of diverse scientific database into the structured knowledge base that we were talking about before. The whole pipeline also ensures an open, reproducible, and scalable pipeline, so it is all aligned with the European open science policies. And that is all for my part. Thank you for listening. I hope I was clear enough, and I leave the floor to my colleague, Aida.
Thank you so much. Thank you very much, everybody. Everybody for listening, and thank you, Achille. Thank you, Miriana, for your presentations. You've introduced a few topics that I would need to talk about, so it's easier for the listeners as well. So this next section of the presentation actually talks about the next step after extracting all the unstructured information or the structured information from the unstructured texts. What do we do with this once we have built the knowledge base or the knowledge graph? What do we do with all that data? Then we are trying to introduce some sort of intelligent twin. So we want to make the digital twin smart in a way that it can perform tasks based on that data that we've collected, that data that it's going to learn from. So going from understanding the past to navigating the future with artificial intelligence. And this title means that basically we want to understand the past, and it is all the cultural heritage data that we've gathered and structured, and navigate the future with AI, because we have tasks that extend over not only the present, which is accessing this data, but also the future, which is prediction and foresight and simulation. So from cultural memory to intelligent futures, the cultural memory to intelligent futures would again insinuate to the past cultural heritage data that has been structured, and then moving towards more technological and intelligent tasks. We're opening with a quote that is very striking for the next part of the presentation. It has been said that at its best, preservation engages the past in a conversation with the present over a mutual concern for the future, by William J. Mutra. And this quote actually describes perfectly the flow of work between collecting, excavating these artifacts, preserving them, making them, inserting them in a knowledge graph, accessing them, doing tasks on them, querying, and etc. We're trying to move through time with these artifacts, preserving not only the objects themselves, but also the stories they tell, and using those to make sure that these artifacts or these cultural heritage elements never disappear. The following work builds on this foundation, which enables users to interact with the query, the knowledge graph, in a natural language, so English, plain English for now, using AI to fill any blanks. This is going to be discussed further in detail. And interacting with the knowledge graph would be the present time, foreseeing possible deteriorating events affecting the tangible cultural heritage using predictive AI. So in this point, we would like to predict what might happen to this cultural heritage, for example, based on the data that we've already gathered, that it's already learned, for example, cultural context, historical context, what might happen, and if there's something that's deteriorating, can we know that beforehand? Simulate scenarios and test ideas that explore the potential futures of cultural heritage using AI, as you've seen in the introductory video. This point would be to not touch the actual tangible cultural heritage, but rather do all the tests and simulate all the possible scenarios on a digital version, which makes us able to maintain and preserve the original, and also go back in case something goes wrong. The ability to redo or to undo what's been done. Why does this matter? Why should we use this technology? Why is it worth putting any time and effort in? Cultural heritage data, as Miriana had said, is vast, complex, and often scattered. So it narrates a story. It's very detailed. Each element is connected in a very specific way to another element. All the relationships are very detailed, and ontologies oftentimes try to generalize these relationships, but they still are quite granulated. So it is a little hard to just query it as a normal, for example, normal graph would be with clear relationships, very distinct relationships. And so this requires a certain tool. querying needs Sparkle knowledge. If you want to query these complex knowledge graphs, you would need to use knowledge graph querying language, which is Sparkle. But if you want to make users limited by that, then it limits the access to just experts, to just specialists that have this knowledge of Sparkle. Lack of explicit links. As we've said, the cultural heritage data is sparse, and sometimes data is not available. Sometimes providers don't provide certain details. There's links that are missing in the data. And as much as with Miriana's work, we are trying to extract this information as best as possible from these unstructured text documents. We're trying to fill all these blanks already before we are building the knowledge graph. But if the information is not also in the text documents, it cannot be extracted. So at the end of the day, those links may still be missing. So we have gaps in retrieval. Sometimes you want to query something, and since there's not that link, you will not get that result. So why we're using AI is indeed to connect these dots. AI helps identify patterns that are not explicitly present, but we can infer it through the structure, composition, and semantics. And this is using AI models. AI's forward-looking capacity as well makes digital twins become more laboratories or resilience and foresight. So in this case, we're looking for the foresight and simulation of all the scenarios. So using AI not only connects the dots, but also lets us test and look at how the future is for these artifacts and for these cultural heritage elements. The approach for querying. The first point is querying, and the approach suggested and implemented for this is in the following structure. So from natural language to smart graph querying. So you notice how we've moved from Sparkle language, which is graph querying language. It requires actual specific technical knowledge. We want to make access to this data more broad to anybody who might want to query this knowledge graph. So we are using natural language, plain English. The input is as the user enters a natural language question, describe as they want. A generative pre-trained transformer adds a semantic and ontological structure. What we mean by this is after we have the question from the user, this question contains keywords, contains key elements. And with the GPT, we are extracting. GPT uses large language models for natural language understanding. And so we are extracting these elements in order to understand what the user wants. And from those elements, we know, for example, that there's a place in question, that there's an object that the user wants to know, that there's a period. All of these have specific categories, let's say. And so the GPT that has knowledge on the ontology that the knowledge graph uses, it can actually structure this user query into a query graph. So we have all the elements, and then it creates the relationships between them. Then the graph is traversed in a semantic way. It's traversed in a way that we are looking for matches, for example, for the elements that the user has actually explicitly stated in the query. Once those results are retrieved, there's an additional step, which uses the AI model now, CompGCN. CompGCN is an AI model. It's a graph convolutional network, which works in a way that it learns nodes, so the nodes, the elements of the graph, and the relationship that ties them together. So in this case, what we mean is that, for example, an entity of the graph has a specific relationship to another, then this link right there is embedded. What we mean by embedding is transformed into a numerical representation, as we see on the diagram on the right. So we have the query, we have the graph embeddings, which are the numerical representations, and we have the query embedding, which is also a numerical representation for each of the things. Now, how does the CompGCN actually work in the query? After having query embedding and graph embedding, a similarity computation is performed on these two things. Similarity computation uses, for example, cosine similarity or other computation methods, and it gives a score to each of the embeddings compared to the query graph embedding. And so the one that's the highest, so the closest to 1, is the most similar. Then we retrieve the top k most similar results, and we rank them as well. And then we concatenate them with the results found by the matching element, so the matching retrieval method. Matching is the most accurate based on the user's query, and then the CompGCN actually gives us also the similar results that are that could be relevant to the user. And then the output would be a ranked list of matched to similar query results. So how does this work specifically is, as we've said, the order of steps is the exact same. So as an example, for example, the user would say, show me coins from the 14th century in Nicosia. Then the NLP enrichment is going to extract coins, 14th century Nicosia. It's going to construct that query graph and then traverse the graph looking for coins, 14th century and Nicosia, and then the CompGCN embedding is going to look for also anything other similar to this query, because embeddings are not specific to the words that are used, but they can also be using, they can find similarity in like synonyms and things like that. So you could also find Nicosia as similar to another location, and it can also give you those results. Why would this approach work? Natural language interface makes the tool accessible for scholars and non-specialists. Graph embeddings go deeper, have a deeper insight into the semantic relationships beyond the structure. So we are looking for the meaning of the relationships and not just which is linked to which. The fact that we can infer relationships, missing links, we are making this knowledge graph resilient to incomplete data sets. And we're making the query resilient to no results, for example, or sparse result retrieval and ineffective result retrieval. And the great thing about this is that it's adaptable. Not one model that is trained on a specific set of data cannot be used for another thing. It can always be retrained on something. It can always be adapted to another set of data, to another task that we want to achieve. This is a short demo that we have ready from the implementation of the Aquarian feature. So here we have, let me mute this. So here we have the typing of a prompt, find information about coins minted in Famagusta. Famagusta is a mint in Cyprus. And here we see that the backend, so everything that I've just explained is running. We are looking for the answer from the graph. And I will be speeding through this a little bit, just in order to get the results a little faster. And here they are. We have the list of coins that we have been able to find based on this prompt. So you have coins from the kingdom where Famagusta was part of. We have the dates, we have the materials, the names, the types of the coins, and also any descriptions that it might have found in the fields, various fields of the knowledge graph. And also different type of coins from another republic, different types, dates, etc. Same concept. Here we already see a little bit where the similarity, aspect has been working, and it's the fact that in this kingdom, Famagusta was part of, and not exactly explicitly stated Famagusta. So another way to see the similarity computation is that with the help of expert intervention, as usual, now the AI models and everything cannot just fully operate on their own. Experts have to hold their hand and actually validate all the information, validate all the results that they are retrieving in order to make sure that there's no faulty retrieval or things that may ruin actually the whole idea of using AI to query a knowledge graph, because the data is intricate and sensitive. So the AI model can continuously learn to identify and infer similarity between cultural entities at different levels. The first level would be pieces that belong to the same object. So the picture on the left is basically pieces that would be cataloged separately, that all belong to the same object, which is the picture on the right initially before it was fragmented. And basically the AI model can or would be able to find the similarity between these different or separately cataloged pieces based on the metadata that is stored along with them. The second level would be different objects that were excavated at the same site, but from different locations. Excavation sites are really large, and you have different grades, and you have different more specific locations. So if one user asks for what has been found in one location, they may not maybe realize that something similar has been found in the other location. And so with that, the AI model can actually suggest that result in case it might be relevant. Different objects that were crafted in the same workshop. So in this case, it would be just different objects, for example, from the scientific reports, maybe the same material, maybe they've been found from in the same location or different locations, but have been used in some sort of manners or with trade routes. The following one would be different objects made from materials originating from the same place. And this again would be inferred from data of scientific analysis reports. The picture or the illustration would show turquoise objects. We have a turquoise beetle and a turquoise bracelet, I assume. And this turquoise material has been specifically inferred to be found in Hubei province in China instead of, for example, in Mexico or Egypt. So since they have been made from the same material or the same material found in the same place, they can be suggested as a result. The last one would be different objects made by the same artist. Now, we are trying to bypass the problem of the visual constraint. So, for example, there's not images in a data set, or images are not provided for artifacts or objects that are cataloged. And so we cannot sometimes find out that these things have been made from the same artist if one may need to know that information. So from the metadata, the AI model can actually figure that out and find this missing link between, for example, these two objects because of the iconography, etc. So roadmap querying, where are we at with the querying? The current status is that CompGCN has been implemented on a clean Ariadne subgraph because we don't have enough data for ARTEMIS yet, and we invite everybody to provide this data for us. Internal validation against expert curated similarities is needed and is implemented. Pilot integration with query interface. So we have a first try at the query interface. What's next? On short term, we have the use of ARTEMIS data, actual full scale ARTEMIS data with all its different data types and domains, and optimization of embeddings, as it takes quite a bit of time. Midterm, we have multilingual semantic support and extended temporal reasoning. So long-term cross-KJ prediction for reactive heritage digital twins. So these midterm and long-term features would be over actually finalizing that knowledge graph and being able to extend the queries, the query reasoning, and use different, even external knowledge graphs for the matter. Future work. Foresight. As I mentioned before, one of the points or one of the purposes was to predict what might happen to cultural heritage elements. So how this would be implemented is with data integration. So we have a large set of data, document data, so historical context, maybe climate data. We have a bunch of sensors on sites of where the cultural heritage, tangible cultural heritage is. So we can gather all this data and then train the model on finding deterioration patterns to recognize risk factors. And then after that, basically help the experts make decisions. So it's not the AI that makes the decisions. Again, human intervention is highly needed, but the AI can actually maybe find that there might be an issue at a certain point in time in the future and suggest decision taking. Expected results is that we have early warning systems for physical decay, data-driven conservation planning beforehand, obviously, and enrich digital twins as predictive tools, not as just static. So the digital twin, as it is or would be soon, is a static version and only the digital twin itself. But maybe over time and with more implementation, we can enrich these digital twins to predict and maybe even protect in a way the cultural heritage elements. Future work simulation. So we've also talked about simulating different scenarios. Implementation-wise, this would mean that the user would propose hypothetical scenarios, and it could be implemented as in the chat sort of interface. It could be that way because at the end of the day, the AI simulation module would be using the AI model to understand what the impact of such actions, of such changes in environments would do to the tangible cultural heritage. So for example, users would propose hypothetical scenarios, and then this model would apply trained models on historical patterns, material behaviors, contextual knowledge to project possible outcomes. And these outcomes can be either returned to the user as visual or narrative outputs showcasing simulated results and potential risks. So it can be either text describing this would happen and this would happen, or maybe visual, which is always much better. As we see here in the right photo, we have what a light seismic wave, obviously this is just illustrative. A light seismic wave, what would it do to that pillar? Or humidity increase, what would it do to that artifact? And this would be a lot more accurate, clearly. So for the results, it would be scenario-driven decision support for preservation and policy. And AI would be a partner in heritage future planning, which takes a lot of effort and is sometimes impossible for humans to be doing. Thank you for listening. This would be marking the end of the presentation. And if you have any questions, please feel free to send them to us.
Thank you. Thank you so much, Miriana, Aida. Yes, we actually have received a few questions, so I'm happy to read them for you. First one was, I guess, for Miriana. Thanks for the very clear and useful presentation. What range of concepts for extracting scientific terms do you currently use or hope to use?
Okay, thank you for the question. So first trial was actually no range. We just put down scientific relevant concepts. This is a cultural heritage paper. So the information we tried to put there to see how the large language model actually worked without a lot of insight was just the basic one. Then, of course, we refined it and are still trying to refine it based on the ontology that the ontological team is writing. So it's scientific analysis, besides, of course, of the basics information. And so like who did what is the cultural asset, where is it located, and everything related to that. Also, we are focusing on the digital twin related ones. So the scientific analysis, so whether if it's like a spectrogram or an XRF or a 3D model or something else, and the thing related to that analysis. So how was it done? If it's written, by who, where, what are the details of the tools that have been used to perform that analysis, and so on. Of course, there's still room for refinement. And together with that, also, we took the other ontologies of the field. So AUCAT, CDOC-CRM, and all the others. And we actually gave also some examples of the properties and entities to be found. So it was more clear, of course, the actual response. But of course, there's still room for improvement, as always. I hope I answered the question.
Thank you. Thank you, Miriana. So let's move to the following question. Actually, we have two questions by Teodora. So first one, in the context of a museum environment, which are the top audiences who do you think they will use this solution the most? I don't know if Aida or Miriana want to answer.
I can answer first briefly because my part, I think, being it a backend, it's mostly useful for museum workers. So research or archaeologists, sculptors, artists, and everyone working inside the cultural heritage field who needs to have access to a database that is structured and also contains semantic information. So not relying anymore on just a piece of paper or a Word document or even the CSV table, which lack a lot of information, especially for the building of reactive heritage digital twins, but also for every type of storing the data. The best way to go is actually to have a knowledge base backed up by ontologies. Of course, it's not always implemented because it's costly and it requires technical knowledge. But when you can do it, and if you have the possibility to input your data and then let the data be structured by somebody else that knows how to actually structure a knowledge base, and then you have the actual final knowledge base that you can also query in a more easy way, like Aida explained. I think that is a really huge benefit. I don't know, like Aida, I think her implementation could also have a lot of other.
Indeed, I would like to add to that answer. And in this case, basically, the people of interest in a museum, for example, would be using this technology for when they are acquiring new items and cataloging new items. And for example, they don't know a lot about the item in question, and they can actually use the knowledge graph to find these missing links, to find this additional contextual information, but also in the predictive and the foresight and the simulation aspects, because we be in a museum, they are preserving certain artifacts, and anything could happen to the museum itself. But having that sort of prediction aspect or foresight aspect can actually help protect these items in a way, at least warn about possible dangers, and then experts on the field or people on the field would do something about it. And also in the simulation aspect, this could it could be a very great added value, for example, in exhibitions, in the education space of it all, because, for example, the people who are visiting this museum can interact with these items and with these artifacts. They can simulate certain things on them to understand how they are made better, because people cannot touch things at the museum most cases or most times. So it could be nice to be able to interact with the object and see it for how it really is in detail, etc.
Thank you both for the answer. We have a couple of follow-up questions related on the inquiry on the coins. The first one: what happens on forthcoming publications? For instance, an unpublished PhD thesis with a top specialist will know, which a top specialist will know about?
Right. So in this case, if the publications or if the information is published already, it can be used, for example, with Miriana's technology to extract that information, enrich the knowledge graph in a way that then results coming from those publications would also show up for the user. However, if publications are not, or like if the information is not published already, is not available, then the knowledge graph may not have access to it, or Miriana's technology may not have access to it, and so it's never going to be accessible through this technology itself, but rather the user may have to access that information ulteriorly.
Thank you. Thank you, Aida. And then another question. So how do you manage, or might you manage, negation detection? So what about queries such as, are there places in Cyprus where no C14th coin have been excavated?
Very interesting question, Keith. Thank you very much. For this case specifically, it hasn't really come to mind previously, as we are trying to find things and not find things. But yes, in this case, then the graph, the query graph would be Cyprus and 14th century not been excavated will not be detected in that case, because that's not the relationship that we're trying to build. The ontology does not have the no aspect, it does not have the negation in it. So then the query graph that would be built would not be correctly queried correctly on the knowledge graph, and probably you'd have some misleading results, maybe perhaps about actual coins being excavated from Cyprus in the 14th century and not excavated. So that is definitely something to keep in mind for future implementation refinements.
Thank you, Aida. And okay, well, I have another question for you, if I may. So, can these technologies be applied in other contexts besides the cultural heritage sectors? So, to knowledge graphs, I don't know, in the health sector, for instance, or in other sectors. What do you think?
Absolutely. Models such as these are very adaptable, as already mentioned, not because they are just used on this data set, they cannot be reused on something else. Obviously, because of the fact that the ontologies are very specific, they would have to be retrained on other ontologies, but the stack, let's say, of technology would still remain if need be. It's just that the data itself that it's trained on would have to change, obviously, because for healthcare and things like that, maybe you have like hospitals, all these kind of things, and not cultural heritage. So it just changes the data, but the structure can remain.
Thank you so much. Thank you, Aida. I don't know if Miriana or Achille want to add anything on this.
No, I think Aida already explained. It's the same concept because, as I said, the work that I presented is the backbone of what Aida is doing. So the algorithms and tools we're using are not specific for a reason, because otherwise they will function just because you train them just to do that. So it will be what they call an over functioning. So it would actually be like a false result. So we are using general algorithms and tools, and then the specification of them comes from the data. So of course you can refine them and fine tune them based on what your needs are, but you change the data, you can still use everything we presented on other subjects.
Great, thanks. Miriana, Achille, want
Yes,
to say final words?
I agree with the replies of Aida and Miriana. I just want to stress the fact that, of course, these tools are agnostic to any domain. They can be adapted to every case and to every discipline. But what is very important, as Miriana and Aida outlined, is the training part. And behind the training, there is always the human activity. So it's important for to establish this synergy between the humans and the machine. Every time we would like to readapt these technologies to different disciplines in order to have the clearance and the cleanness of the information that this fantastic technology are able to provide us. So I think this is a very important point.
Thank you, Achille. So I would like to thank everyone, starting from, of course, Achille, Miriana, and Aida for their great presentations. It was very interesting topic. So to have some insights of this experimental work we are carrying out in the context of the ARTEMIS project. Thank you to our team at Prisma, Ginevra, Brian, and all the team for setting up this webinar. Thank you to everyone for participating, for contributing. We will resume our webinar series now after summer, so we'll stay in touch for the next appointments. I just remind you once again to fill out our survey. You find it on the website and also in the chat on YouTube. It's 5 minutes. Please help us in sharing your thoughts. And well, I wish you a lovely summer and a nice evening, and bye everyone.
Bye, thank you.
Thank you.
Thank you. Bye-bye.